Another way you can determine the rate law, okay, it, if for this simple rate laws, if its rate is equal to K times just the concentration of R raised to the power N, okay. Actually, it's going to be, yeah, and we're just going to assume a coefficient of 1, okay. So let's just get rid of these C's over here. That's a coefficient in a balance equation, so I'm just going to get rid of that, okay. So if the rate is equal to K times concentration of R raised to the power N, okay, you can use what's called a half-life analysis. By plotting R, the concentration of R versus time, and you examine what's known as the half-life, you can actually determine your rate law, and you can determine what the value of your rate constant is based on the half-life. Okay? So the half-life is the time it takes for the concentration to be cut in half. Okay? In the case of a zero-order reaction, okay, you'll find that the half-life gets longer, okay? I'm sorry, it gets shorter it gets shorter the more the reaction has progressed, okay? As the concentration of R drops, your half-life drops. The time it takes for that concentration to get cut in half gets shorter, okay? Whereas if it's a first-order reaction, you'll notice that your half-life is a constant. Okay, it doesn't matter what your starting concentration is. It doesn't matter what concentration you're at. The time it takes for that concentration to get cut in half is the same. It's constant. That's how you can tell it's first order. Finally, if it's second order, n equals 2, you will find that the half-life is inversely proportional to the starting concentration. In other words, the higher your starting concentration, the shorter the half-life. So as the reaction progresses, what happens as the reaction progresses? Your concentration drops, right? So it's going to take longer for that to get cut in half. All right. So those are the consequences of these rate laws. Okay, so your half-life is, okay, this one, what happened? What did you say happened here? It gets shorter, right? As the reaction progresses. If it's first order, it's constant as the reaction progresses. If it's second order, it gets longer as the reaction progresses. Okay, so let's see what happens there. Let's look at this one. Based on the half-life here, what's the order of the reaction with respect to R? Is it 0, 1, or 2? Okay, how do you determine the half-life? Let's look at right here when the concentration is 0.01. What's half of 0.01? What's half of 10? 5, so 0.005. Okay, where is 0.005? Right here. So how long did it take to go from 0.01 to 0.005? 25 seconds. Okay, so when the concentration of R, if you start off at 0.01, your half-life is 25 seconds. Okay, now when my concentration of R is 0.05, what's half of 0.005? 0.0050. Let's make it that way. What's half of that? Half of 50 is 25, so it's going to be 0.0025. Where would 0.0025 be? Here's 0.002, here's 0.003, 0.0025 is over here, and oops, what happened? Okay, 0.0025. Okay, that's 0.003 right there. So this is 0.0025. That's that one right there. So to go from 0.005 to 0.0025, how long did it take? 50 seconds, right? The half-life is 50 seconds. So when your starting concentration gets cut in half, what happens to your half-life? It gets longer. Okay, so we say the half-life is inversely proportional to the starting concentration. So is this thing zero order, first order, or second order based on the information I gave you earlier? It is second order. Okay. If, as the reaction progresses, the half-life gets longer, it's second order. Okay. In fact, if you multiply half-life times the starting concentration, 25 times 0.01, okay, that's going to be equal to 50 times 0.005. Remember your Boyle's law? P1 V1 equals P2 V2. Whenever the product of two things is a constant, we say they are inversely proportional. So the half-life and the concentration are inversely proportional if the order of the reaction is second order. So if I were to ask you, what if I were to start at 0.008? Is my half-life going to be, okay, so what if I start off at 0.008 over here? Is my half-life going to be R equals 0.008 based on this data? Is my half-life going to be less than 25, equal to 25 seconds, or greater than 25 seconds, or greater than 50 seconds? A, B, C, or D? Let's do that. What do you think is my half-life? It's gonna be, oops. Okay, let me elaborate on that a little bit. We've already established this is second order, right? The half-life gets longer the smaller your starting concentration. Okay, so when I said my starting concentration was 0.01, what was my half-life? 25 seconds. So if it's 0.008, and we did what? 0.005, it was 50 seconds. What do you think this number is going to be in between? As the concentration drops, the half-life gets longer. So what's the best answer? Try it again. Okay, much better. Okay, correct answer is C. In fact, you can figure it out. What should it be? We're going to say 0.010 times 25 must be equal to 0.008 times x, right? But got half-life there. So what would the half-life be? X would be 0.010 over 0.008 times 25. What would that be? 31.25 seconds. Okay, 31.25 seconds. Let's see if that's in fact the case. Let's look at our graph. From 0.008, what's half of 0.008? 0.004, right? So that should be about 31 seconds approximately. Is that about 31 seconds? Yeah, that's a little longer than 25 seconds, right? So. Now, how do you determine the rate constant? Let's go back to our equation here. The rate constant, okay? And like I said, I'm just going to get rid of that C. If it's second order, from the half-life, you can get the rate constant. The rate constant, how do I solve for K here? K equals 1 over R naught times the half-life. Okay? So that would be the rate constant for a second order reaction. So going back to our example, what's our rate constant? Our rate constant is Our second order rate constant is 1 over R naught starting concentration times the half-life. Okay, so that's 1 over, what's our starting concentration? 0.010 moles per liter. And our half-life was 25 seconds. So that's equal to, what's 1 over 0.01 times 25? 0.01 times 25 is 0.25. So 1 over 1/4 would be 4, right? So this is going to be 4. And what's the unit for our rate constant? Per molarity per second. Okay? That's the unit for a second order rate law. That's your rate constant right there. So your rate law, we say, is, you write your rate law, you say rate is equal to the rate constant, which is 4 per molarity per second, times the concentration R raised to the second power. Okay, so that's how you can tell what your rate law is. Okay, let's take a look at this one. Based on the half-life, what's the order of the reaction with respect to R here? Let's see, how long did it take to go from 0.01 to 0.005? So when R is 0.01, what's our half-life? 25 seconds. How long did it take to go from 0.005 to 0.0025? So this is 0.002, that's 0.003, so 0.0025 is over here. How long did it take? If you're starting off at 0.005, how long does it take? Another 25 seconds, right? You have to start counting from where you start, from where you're starting. So it takes 25 seconds. So based on this information, is the order of the reaction 0, 1, or 2? It's first order. Okay. Going back right here. Okay. Look. Gets longer if it's second order. The half-life is constant. Okay. Let's clear this out for you. The half-life is constant if it's first order. So in fact, what is our rate constant here? This is first order, so n equals 1 here. So how do I solve for my rate constant? It's just equal to natural log of 2 divided by the half-life. So from the half-life, I can figure out what the rate constant is. What's the value of natural log of 2? It's 0.693. So 0.693 divided by the half-life. Okay? So let's look at this one right here. What is our rate constant here? Natural log of 2 divided by the half-life, which is constant. So it's 0.693 divided by our half-life, which is 25 seconds. How much would that be? 0.693 divided, oops. Okay, here, by the way, if you want to know what ln of 2 is, 2, take ln of that is 0.693, okay? So ln of 2 is 0.693 divided by 25 seconds. That's 0.0277, 0.028, okay? And what's my unit for my first order rate constant? Per unit time, so per second. So you'd say the rate law for this reaction is rate equals 0.028 per second, that's my K, right, times the concentration of R raised to the power 1. That's my rate law.